Hello students, welcome to EPG Pathshala. I am Professor P03 from Jammu. Today we are going to discuss about a module entitled Experimental Crystal Growth under paper Crystallography and Crystal Growth. So students, let us see what we are going to learn in this module. We will be learning about the main categories of crystal growth methods. Growth from water solution and its advantages and disadvantages. We'll be talking about low temperature solution growth and what are the requirements of an ideal solvent. We'll be discussing about habit of crystals, the solubility of material and the apparatus for crystallization, slow cooling technique, solvent evaporation technique and temperature difference technique. Now let me talk about the experimental aspect of crystal growth. Successful growth of crystals require strict control over phase change. There are processes involving growth of solute from phase transitions, namely liquid to solid state or vapor to solid state or solid to solid phase transitions. Main categories of crystal growth methods include the following. A. Growth from solution. In this major category, there are certain subcategories like A1, growth from flux, A2, hydrothermal growth, A3, high pressure growth, A4, growth from water solution, A5, growth from gel. A.6, other innovative techniques which fall under subcategories of related growth techniques include organic solution growth, accelerated crucible growth, electrocrystallization, liquid phase epitaxy, and molten metal solution growth. The next major technique is growth from melt. There are subcategories. In this category, like Czochralski crystal pulling technique, Vernier flame fusion growth technique, Bridgman Stockburger growth technique, and crystal growth by zone melting. Other innovative techniques that fall under subcategory of related growth technique include plasma melting, liquid encapsulation pulling, skull melting, normal freezing, directional freezing. Now the third major category of crystal growth is growth from vapor phase, in which there are categories like gas phase reaction method, chemical vapor deposition method, vapor phase epitaxy, and gas transport processes. Halide transport processes, sublimation, vacuum evaporation, molecular beam epitaxy, temperature oscillation method. Now the last major category is solid state growth. In this there are subcategories like sintering method, zone heating method, strain anneal, polymorphic phase transition, and solid state diffusion reactions. Some of these techniques, which are widely used, may be described in a slightly more detail. We shall first take up growth from solution. In this method of growth, the components of the crystal to be grown are dissolved in a solvent so as to form a saturated solution. The solution is made supersaturated by evaporation of the solvent or by changing the temperature, which results into crystallization of the excess material. There are two types of solution growth, one being low temperature solution growth and the other being high temperature solution growth. Growth from solution yields crystals, usually with well-developed habit phases as it happens with natural crystallization. Many commercial materials like sugar, salt, hydrated materials, several materials that decompose before melting, and several good quality crystals meant for electronics and optical industries are grown from solution. Potassium dihydrogen phosphate, abbreviated as KDP, ammonium dihydrogen phosphate, abbreviated as ADP, optical grade sodium chloride crystals, and several others are grown from aqueous solutions. Quartz, a optical, electronic, and high Q value grade of quartz are grown using hydrothermal crystallization technique, whereas magnetic bubble domain materials and several useful oxide crystals are grown using flux method. Growth from water solution. In contrast to high temperature solution method, to be discussed later, growth from water solution is directed at producing a crystal by growth from solution at low temperatures of materials which have moderate to high solubility in the temperature range ambient to somewhere around 353 degree K and at atmospheric pressure. Growth of crystals from low solubility systems or under high pressures fall under other specialized techniques, details of which are described in the relevant sections. Advantages of growth from water solution are as follows. Number one, since crystal growth from solution occurs at ambient temperatures, one can exercise a better degree of control over the growth conditions. Number two, temperatures can be easily stabilized in this range. As a result, supersaturation can be accurately and precisely controlled. Number three, the proximity to ambient temperatures reduces the possibility of major thermal shock to the crystal both during its growth and completion of growth. Number four, it allows growth of crystals under closely controlled equilibrium conditions and at not very high temperatures, consequently resulting in the minimum of both equilibrium and non-equilibrium defects, and in several cases to almost zero. Number five, the method is particularly useful for the growth of those materials which decompose in the melt or in the solid at high temperatures and which undergo phase transformation above the working range of crystallization from solution at low temperatures. Such materials include several organic and inorganic substances. Number six, different morphologies and polymorphic forms of the same substance can be obtained by variation of growth parameters or of solvent. However, this category of growth method suffers from some major disadvantages, as for example, number one, possibility of solvent inclusion. Number two, slow rate of growth of crystals in several cases. The disadvantage identified at serial number 1 can be overcome to a reasonable level by better control of growth conditions. There are two basic techniques which are used in the growth of large crystals from water solution. In both cases, a saturated solution is first prepared and a seed crystal is inserted. In one technique, the temperature is lowered slowly so as to reduce the solubility leading to crystallization. In the second technique, the temperature is held constant, but the solvent is permitted to evaporate leading to crystallization. Vigorous stir is required in most of the cases, and many variations on these two general techniques are possible. Several crystals like gadolinium aluminum sulfate hexahydrate, Rochelle salt, glycine sulfate, sodium chlorate, potassium alum, sodium bromate, sodium nitrate, triglycine sulfate, potassium dihydrogen phosphate, ammonium dihydrogen phosphate, and several others have been grown by this method. In order to be able to achieve maximum potential of this technique of growth, it is important to make choice of a suitable solvent and use ultra-pure materials. The ideal solvent should have the following properties and the characteristics. Be able to yield a prismatic habit in the crystal. The most useful crystals are the ones which grow at equivalent rates in all dimensions and lead to large bulk crystals. Number 2, low viscosity. Number 3, density less than that of the bulk solute. It is desirable that the growing crystal does not float. Next, high solute solubility and low volatility so that uncontrolled loss of solvent during the growth period is minimized. Next, high and positive temperature coefficient of solute solubility. The last one concerns the solubility of the material in the solvent and its dependence on temperature. These factors control supersaturation, which is the driving force behind the rate of crystal growth. The supersaturation delta is defined as delta equal to delta C upon C0, where C0 is the equilibrium concentration of solute at the temperature of growth and delta C represents the increase by which true concentration exceeds this. There are different ways in which solution can be supersaturated. One is temperature lowering method. In this method, attempt has to be made to control the temperature controlling rate so as to achieve a constant supersaturation over a wider temperature range. It is versatile and easy method to operate. The second method is known as solvent evaporation technique, in which slow evaporation of the solvent at constant temperature is allowed. If evaporation rate is controlled so that it is held constant, then again a constant supersaturation can be maintained. In practice, it is more difficult to achieve than is a controlled temperature lowering rate. There may be cases in which the solute solubility is very low. The above described methods cannot be employed, and some other methods which allow the precisely controlled slow development of supersaturation could be used instead. In these methods, the supersaturation is achieved either by the slow interdiffusion of solutions of two reacting chemicals which on mixing react to form the solute, or by interdiffusion of a solution with a solvent in which the solute is insoluble or less soluble. The required control over the supersaturation is achieved by controlling the flux of the interdiffusing reactants, that is by varying temperature, concentration gradient, and solvent viscosity. This is the basic principle of gel growth, techniques for the growth of crystals of insoluble salts. This technique of growth will be discussed later in the relevant section. Low temperature solution growth. Crystals grown from solution are by slow cooling or solvent evaporation techniques. Almost 90% all crystals produced by low temperature solution techniques are soluble in water. Obviously, this puts limitations on their use to applications where water and water vapor does not get involved. The requirement for such crystals therefore remains restricted. The crystals grow from solutions which are supersaturated. As the growth takes place, a concentration gradient occurs near the growth phase. Because of this, the growth phase is inherently unstable with respect to supersaturation. In crystals, growth from solution at low temperatures, the crystal is generally immersed in the solution. As a result, the latent heat evolved makes the crystal hotter than the solution. It is an additional factor which increases the supersaturation gradient. Stable growth becomes possible on account of stabilizing influence of surface free energy and the growth kinetics. It is possible of this reason that stable growth phases are always singular in solution growth. However, in seeded growth from solution, non-singular phases occur around seeds obtained by cutting crystals along some suitable orientation or planes, which usually renders the growth unstable. This is the reason that cluster of inclusions is seen around seed crystals. Rates of growth from solution are much less as compared to rates of growth from melt. The low temperature solution growth has been discussed in detail by Buckley, 1951. One could obtain more information by referring to H. E. Buckley, 1951, Crystal Growth, published by Chapman and Hall, London. In this method of growth, solvents and solution should have certain characteristics in order to be effective. An ideal solvent is the one which should yield a prismatic habit in the crystal, have a high positive temperature coefficient of solute solubility, have moderate reversible solubility, be non-corrosive, have a small vapor pressure, have low volatility, be non-toxic, be available in pure state at low price, be non-inflammable, have low viscosity, and have density less than that of the bulk solute. The last two characteristics of the solvent are helpful in the simplification of apparatus design, since it is desirable that the growing crystal should not float and that it should be well agitated. Solvents are required to have low volatility because it reduces the possibility of uncontrolled loss of solvent during prolonged growth periods. It is particularly important where supersaturation is achieved by processes other than solvent evaporation. The first three requirements of solvent characteristics are the most important characteristics which need to be described in some more detail. There is no such single solvent which incorporates in itself all these characteristics. Solvents that are generally used include water, ethyl alcohol, carbon tetrachloride, acetone, hexane, xylene, and several others. However, water is used in most greater than 90% of the cases. Habit of crystals. Crystals which grow at more or less equivalent rates in all dimensions, popularly known as equidimensional crystals, are the most useful ones. From the research point of view, also such crystals are quite informative regarding orientation, microtopography, and so on. Also, if the crystal grows with large habit phases, the defects which generally get generated either from nucleus or the seed and propagate along specific directions into the bulk of the growing crystal usually become isolated into defective regions surrounded by large volumes of very high perfection. If the crystals grow in the form of needles or plates, the growth dislocations follow the principal growth directions with the result that crystals get imperfect. It is more so for crystals which grow in the form of needles where the defects propagate continuously into the whole body of the crystal. Variations in the habit of a given crystal do occur with the variations in solvents. Next we come to solubility. The major factors involved in crystal growth from solution are the solubility of the material in the solvent and its dependence on temperature. The former provides the amount of material which is available for growth and hence defines the total size of the grown crystal. Both the solubility and the temperature define the supersaturation, which is the driving force that controls the rate at which the crystal grows. The supersaturation delta is defined as delta equal to delta C upon C0, where C0 is the equilibrium concentration of the solute at the temperature of growth and delta C is the increment by which the actual concentration exceeds this. Supersaturation in a given solution can be achieved in many ways. One is to lower the temperature of the solution below the equilibrium saturation temperature. It is popularly known as temperature lowering method. In this method, the temperature is lowered continuously at a controlled rate, and delta C is determined by the rate at which temperature is lowered. In case of linear variations, delta C remains constant over small temperature intervals, subject to the condition that the solubility temperature curve does not change its slope very rapidly. However, it is not difficult to match the temperature lowering rate to the desired shape of the solubility curve in order to make it possible to achieve a constant supersaturation over a wide temperature range. This method is the most versatile and a convenient one to operate. The second method is constant temperature differential method. In this technique, the temperature is suddenly lowered. Difference between the two equilibrium values is delta C. The value of delta C and thus the growth rate will decrease as growth progresses. So one has to replenish the solution saturated at the upper temperature constantly as growth proceeds. Though much more complicated than the first method, that is the temperature lowering method, it can still under some situations and is a means of growth under rigidly constant temperature supersaturation conditions. The third method is to allow the slow evaporation of the solvent at constant temperature, and the technique is popularly known as solvent evaporation technique. In this method, constant supersaturation can be maintained by controlling the evaporation rate at a constant value. In terms of practical feasibility, it is more difficult to achieve as compared to controlled temperature change. Which of the methods of supersaturation are to be applied depends to a very great extent on the shape of solubility curve and magnitude of solubility. For this, one is required to have full knowledge concerning solubility temperature data. Let us consider a solubility curve of figure 26.1 in which the material changes its solubility rapidly with temperature. The curve is divided into three major regions: high, moderate, and low. The region marked by capital M corresponds to moderate high solubility and moderate solubility temperature gradient, and so is a region which is suited for the use of temperature lowering method. To further discuss this, it is required to have solubility data for some materials as tabulated below in table 26.1. It is found that if solubility falls in the range 200 to 1000 gram solute, and that the ratio of solubility dash temperature gradient to solubility, that is solubility ratio, falls in the range 0.03 dash 0.01, good quality crystals can be grown at temperature lowering rates of 0.5-1 degree per day, that is at supersaturations of the order of 2%. It requires a greater degree of temperature precision, plus minus 0.005 K, to ensure that there are no sudden fluctuation, which ensures prevention of sudden bursts of faster rate of uncontrolled growth, which leads to imperfect crystals. In case of solubility and solubility gradient exceeding this range, as for example at capital L, it is important that the system is controlled with great precision. Small fluctuations in temperature will lead to large fluctuations in solubility, supersaturation, and growth rate. It therefore demands a better precision of the temperature of the order, say plus minus 0.001 K, in order to bring down these variations for systems at the lower end of capital L range. If such a precision in the system does not become available, one may use constant temperature differential method, in which the temperature of both source and growing crystals can be maintained at precisely controlled constant values. The curve of solubility versus temperature is shown in figure 26.1. Let us now come to the region capital N. In this region of rapidly changing solubility gradient, it is difficult to maintain constant growth conditions even for short periods of time. In the region O, the gradient is shallow and the delta C achievable by either the temperature lowering or constant temperature differential techniques is greatly reduced. Obviously, the growth rates will be low and even slight fluctuations would greatly affect growth parameters. It is desirable to use solvent evaporation technique to achieve reasonable level of supersaturation. The solvent evaporation method is very effective in such cases where the overall solubility is low. In such cases, the occurrence of fluctuations brings about only small fluctuations in supersaturation, and so the growth process does not get affected much. Following the above said general guidelines, one can identify the suitable solvent and the appropriate technique of growth and use the same to grow a crystal of large dimensions. Let us discuss the low temperature solution growth further in the background of some information provided in table 26.1. There is a specific classification of materials under the categories of easy to grow, difficult to grow, and growth improved by varying conditions. The first category gives examples of materials which can be relatively easily grown to obtain crystals of large dimensions by temperature lowering method or constant temperature differential method, and at temperature lowering rates in the range of 0.1-1 K per hour, subject to the condition that the apparatus used for growth is able to maintain temperature stability of more than plus minus 0.005 K over long periods of time. The materials like sodium chloride, benzyl, calcium carbonate, and silver iodide are relatively difficult to grow. The third category of crystals are the ones whose growth process can be improved by varying conditions of growth. The quality of crystals of anthracene, urea, with water and methanol as solvent, and several such organic and inorganic materials is worse as compared to those belonging to first category of crystals when they are grown at similar rates close to ambient temperatures. Preliminary experiment. To grow a well-formed single crystal of the desired substance, one has to make a solution which is saturated at room temperature and then allowed it to evaporate in order that as the solvent evaporates, some of the substance in solution will have to be deposited so that the solution does not get supersaturated. If one desires to grow crystal of a particular substance, it is necessary to have knowledge about its solubility and then calculate the relative amounts of solute and solvent that is required to make a saturated solution. As for example, we may take the case of alum, whose chemical composition is KAlSO4 twice, 12 times water. The first step is to study the table that provide information regarding solubility of alum, which is about 11 grams in 100 milliliter of water at a temperature of 20 degrees centigrade and at 100 degrees centigrade. Its solubility is extremely large. One can therefore make a solution of alum by taking approximately 15 grams of alum in 100 milliliter of water. Put this solution into a beaker, heat it with constant and vigorously stirring it. The hot solution may be filtered to obtain a pure solution. Place the solution in the beaker, which is slowly covered, in order to allow water to evaporate without allowing the dust to enter into the solution or get contaminated in any way. After a few days, one would find some alum having deposited as small crystals. Take one of the small crystals and suspend the same with the help of a string thread so that it remains immersed in the solution of alum as shown in figure 26.2. Allow water to evaporate. As water evaporates, the crystal will start growing in size. Allow 1 or 2 weeks for the crystal to grow. One would find the growth of alum crystal having increased in its size and developed into a regular octahedron. It would take a week or two for the crystal to grow to a large size. Table 26.1 is the table which provides data on solubility S and solubility temperature gradient ds by dt for some organic and inorganic materials. It provides information on the category of materials which are easy to grow, difficult to grow, or growth improved by varying conditions. The materials considered are sodium chlorate, sodium bromate, and many others which are easy to grow. Then sodium chloride, benzyl, calcium carbonate, silver iodide, which are difficult to grow, and urea and adipic acid, which are growth improved by varying conditions. Then the list of solvents is provided. The solubility gram per 1000 gram of solvent at 303 K is provided. ds by dt is provided. ds by deta by S is given. Temperature for good growth is also given and compiled in table 26.1 for some material. Figure 26.2 is a schematic diagram showing a simple arrangement for growth from water solution. The apparatus for crystallization, the method for producing large single crystals from solution is the temperature lowering method. Different types of apparatus designed for the production of large crystals of organic and inorganic substances from saturated solution at low temperatures are many and are described in the literature. Pamplin has listed a large number of references that are available on the subject. The variation in design of the apparatus depends on the ultimate size of the crystal that one may wish to grow, nature of the solvent, phase, and other related parameters of growth. However, there are certain basic requirements for the growth apparatus which have to be common to all. These are temperature control to better than 0.01 K. The thermostatic control may preferably be somewhere in the range of 0.005 to 0.001 K. Vigorous stirring of solution. It would ensure prevention of layering and spurious nucleation. Then efficient reciprocated stirring of the crystal. It is necessary for the prevention of local supersaturations or undersaturations which become the cause of variations, that is increase or decrease in the rate of crystal growth and leading to incorporation of solvent and wheeling. Then arrangement for controlled supersaturation of the solution. We shall describe solvent evaporation technique. Slow evaporation is most easily achieved by using a controlled flow gas inlet, oblique outlet attached to the head of the flask and a trap to collect the condensing liquid. One is confronted with a practical problem, and that is to ensure a constant desirable rate of loss of solvent from the system. A system for growth by solvent evaporation is shown in a schematic diagram of figure 26.4, which meets the above requirement of acceptable rate of loss of solvent from the system by providing a cooled condensation region. Alternative method is to use porous covers separating the saturated vapor above the solution from a large and well-stirred volume of air with a negligibly small partial pressure of the solvent. The porosity of the covers may be in the form of holes or tubes or a permeable membrane. The porous covers can also be in the form of cellulose fiber sheets, say cellophane, are very useful as they allow water to go out while protecting the system from dust and external particles. The rate of loss of vapor through the membrane can be varied using a non-porous cover over part of the membrane area. Solvent evaporation process produces crystals of limited size, as is the case with slow cooling process. However, crystals grown by solvent evaporation are less pure as compared to crystals grown by slow cooling process. It is because with solvent evaporation, the concentration of impurities in the solution has tendency to increase as growth proceeds further. Figure 26.4 is a schematic diagram of an apparatus for the growth of crystals by solvent evaporation process. The apparatus shown in figure 26.4 has provision for holding seed crystals. In fact, more than one seed crystal can be used by cementing each of them to one of the holders attached to a multi-arm assembly named spider. The spider can be rotated both in the clockwise as well as anti-clockwise directions. The solution is thus continuously stirred, which helps to avoid interface instability and spurious nucleation. Typically, the spider is made to make 4 revolutions in one direction, stop for a while, and then allowed to make 4 revolutions in the opposite direction. The cycle is composed of making revolutions in one direction, pause, then making revolutions in opposite direction, another pause before repeating the cycle. Each cycle keeps on repeating during the experimentation of crystal growth. The maximum RPM depends on the width of a crystal and radius of its rotatory movement, and the Reynolds number as required is calculated, which usually should be at the most less than or equal to 2000. Temperature difference technique. A simple apparatus which works on the basis of temperature difference process is shown in a schematic diagram of figure 26.5. In this arrangement, the crystallizer is divided into 2 zones, one cool growth zone and the other hot nutrient zone. Seed crystal is maintained at temperature capital T, which is lower by delta T as compared to the upper nutrient zone. The nutrient zone being maintained at a temperature T plus delta T. The solution is almost saturated in the zone at T plus delta T, while the seed crystal maintained at temperature T will grow. The amount of growth is limited only by the amount of nutrient which is put into the hot zone of the crystallizer. One could, in principle, think of adding more nutrients during the growth run, but then to maintain the temperature at T plus delta T requires much more care. The above apparatus is a simpler version of temperature difference crystallizer. In those systems which are used for production purposes, the cool growth zone is separated from the hot saturator. The solution is pumped from one vessel to the other. Supersaturated solutions have a growth zone separated from the hot saturator. The solution is pumped from one vessel to the other. Saturated solutions have a tendency to nucleate when pumped, and if solution saturated at T plus delta T is pumped directly to the growth vessel, it makes a way for undissolved particles to get transferred to the growth region. To avoid this from happening, 3 vessels are used in place of 1. If this is not done, the undissolved particles will enter the growing crystal and render them imperfect. It is claimed that the growth of really large crystals is most likely to be achieved in systems of this type. However, if one is to deal with large volumes of liquid exceeding 100 liters, it is extremely difficult to provide suitable degree of mixing and to avoid convective instabilities. The use of slow cooling processes is used in a large number of crystal growth experiments from solution. They are in several ways simpler than the processes involved in solvent evaporation or temperature gradient transfer. In this process, only one vessel is required, and the most important requirement is to meet the major technological requirement of providing the desired rate of cooling as precisely as possible. On a commercial scale, the volumes of solution used are quite large, namely in the range of 10 to 100 liters. However, in the current demand of P04 of 300 dimensions, even larger volumes of solution may be required. Figure 26.3 shows the design of a simple crystallizer for the growth by slow cooling method. It consists of a double vessel system, stirrer, and water inlet oblique outlet, mechanical arrangement for rotation of seed crystal holder, and insulating platform. There is an external temperature controlled bath from which water is pumped into the water jacket so as to maintain the solution at the programmed temperature. In order to ensure circulation of the solution, multiple stirrers are used. In figure 26.3, only one stirrer is shown. There is a provision for placement of seed crystal on a holder which is in the form of a disc. The seed crystal is mounted on this disc which can be rotated. It is rotated in a particular direction, say clockwise, for some time and then rotated in the reverse direction, say anti-clockwise, for some time. The number of rotations per minute, that is RPM, is maintained appropriately after careful calculations. In using the technique of growth by slow cooling, it is necessary to maintain temperature stability. Interface instability due to any reason results into inclusion formation and spurious nucleation. The instability is mainly caused by short bursts of rapid growth as a consequence of fluctuation in temperature. Growth rate variations can as well be caused by other parameters like fluctuation in the amount of stirring. Rotation of the seed in two opposite directions does reduce the possibility of spurious nucleation to a great extent. So, students, let us summarize what we have learned in this module. We have learned about the major method of crystal growth techniques which have been characterized. Growth from water solution and its advantages as well as disadvantages are described. Low temperature solution growth is explained and requirements of an ideal solvent are given. The solubility requirement of a material are given. The apparatus for crystallization of materials using slow cooling technique, solvent evaporation technique, and temperature difference technique are described.